All right, so here we're going to work a problem. We want to determine the maximum moment created at B, which just happens to be right in the middle of the beam. And it's going to be due to this very simple little wheel load. Maybe this is a truck or a cart of some kind. And it's on the right side of the structure and it's traveling to the left. And you can see that the wheels, I didn't visualize the upper part of the structure, just the wheels. You can see the front wheel is a 2-kip load, the back wheel is a 5-kip load, maybe a pickup truck of some kind. So 2 loads at 12 feet apart, moving from right to left. I want to find the maximum moment that occurs at B. So what's the first thing we have to do for that? We have to find the influence line for the moment at B, right? Now remember, if we're using Mueller-Breslau, what does it say? We're going to come in, we're going to assume, or visualize, I should say, that the middle of the beam, B, doesn't have the ability to withstand moment. So I'll put a hinge there. And then remember that we, again, visualize positive bending moments being applied to both sides. And how will that point be in this virtual space move? Will it move up or down? What do you say? So it will move up. So we know the shape of our bending influence line. And how many values do I need to establish on this curve to know everything? Just that one peak value right there in the middle. So what does that translate to? That translates to a simple supported beam with the influence with the unit load right slap in the middle. I'd have a reaction at A, a reaction at C. The dimensions here are, let's see, it's 100 feet. Now, I am then going to cut that structure right there at C, decide if I want to work the left or the right-hand side, and try to find the internal bending moment. That will give me this value right there. Which side do you want to work, the left side or the right side? Left. So if we want to work the left side, we need to find AY. How do I find AY? Probably some moments at C. So let's some moments at C, make sure it's in equilibrium. With right-hand rule as our sign convention, what's the moment created by the unit load? Positive. So that'll be a value of force of 1, a moment arm of 100 feet. And then AY creates negative moment, and it has a moment arm of 200 feet. So it looks like AY is equal to 1/2. That doesn't seem that far off. I mean, you have a load right in the middle. You'd expect half to go to each side. That seems reasonable. And now I'll cut that structure at C. AY has the 1/2 reaction. And at 100 feet over, I'm looking at the internal moment at B. How do I find the internal moment at B? No? Yeah, we just sum moments again, right? So I'll sum now at the cut that I just made in this section. Make sure it's in equilibrium. And what do we have? Well, with right-hand rule for our sign convention, this internal moment is positive. And the 1/2 creates negative. So I've got a force of 1/2 times a moment arm of 100 feet. So it looks like the moment at B is equal to 50 feet. So now I can draw the moment at B. This will be the influence line. Here's the general trend. We knew the shape already, the qualitative shape from our Mueller-Breslau principle. And now I know that middle value is 50. And all the units on this are feet. Okay, so do the influence line for the moment at B. Now, how do I solve the problem? Well, my vehicle, my two sets of live loads are starting on the right-hand side. They're moving to the left. So there's two loads, so there's going to be two cases. The first case, we're going to let the first load, the lead load, come across the structure, and where should we stop it to create the maximum moment at B? Looks like at B, right? So here's case 1. Give me a second here to redraw the influence line so that you can see this stuff. I will change the scale a little bit so I can fit some things in. So now my wheel load comes over, and the first load, which was 2 kips, lands right at the top. And then 12 feet back is the rear wheel load, which is 5 kips. And you can see it intersects with certain values on my curve. So I already know that this is 50, this value right here. What's the value there? What's the slope of this line? Well, rise, which is 50, over run, which is 100. These are both in feet. So it looks like the slope is 1/2. That's not right. Yeah, that's right. So that means that every foot I move, my value drops by 1/2. And how many feet am I moving to the right? 12. So I would drop, half of that is 6. So this will be 44. Remember, the units of this are in feet. So how do I find the moment at B? I take my 2 kip times 50, so this will be 2 kips times 50 feet plus 5 kips times 44 feet. What's that equal to? 320, I'm guessing.
Why do you do the moment?
Why do I do the moment at B? That's what the problem asked for, moment at B. I drew my influence line for the moment at B.
And it was 50. So then what do you do now?
I am finding the effect of this set of moving loads on the moment at B. I'm putting the first load at the maximum point. That's where it's creating the maximum effect. And of course, 12 feet back is the back load. And it's at this position, so this is the value there. Yeah?
So, why the 2 kips times 50? Because that from the moment it was the force.
Well, 2 kips times the height of the influence line, which is 50 feet. Right? That's the way we always do it, right? You take the force times the magnitude of the value of the influence line. But since I'm putting the first load at the maximum value, the second load, I can't move it to the maximum value yet because it's always 12 feet behind the first one. So case 1 would be letting the first load make the maximum effect. Case 2 is we're going to let the vehicle move to the right or to the left, and the 5 kip will be sitting on top. So we have to have a case where each of the loads in our set, this only has 2, I could have 3, I could have 4, I could have 5, I could have 100. And I have to let each one of those get an opportunity to create the maximum moment at D by being, in this case, right at D. Because we found that when you're at D, that's when you create the maximum moment at D as a unit load. What's this numerical value?
6.
And that will be kip feet. So let's do case 2. See if I can squeeze it in here. Just takes a little. Give me a second to redraw everything. So there's my influence line for B. That hasn't changed. But now the truck moves to the left, and the rear wheel now is at the middle. 5 kips. And 12 feet in front is the 2 kip force. So what's the value of the influence line right here under the 5 kip? We've already figured that out. That's 50. Right? And what's the value 12 feet in front? Well, the slope of both these lines are the same. They're both 50 over 100. So the same logic we used to figure out that this was 44, it's going to be 44 in the front. So now this case, I'll call this case 1. So the moment at B due to case 2 will be the 2 kip force now times 44 feet plus the 5 kip force times 50 feet. 250. I think that's more than 320.
338. 38, sorry.
38?
Yes, sir.
So just barely a little bit more. So now we'll say that the moment at B max for this system will be the larger of the two, which is 338 kip feet for this vehicle.
So when you ask on the test us to do something more with the influence line, that's kind of what you mean?
Right.
Okay.
Now what we did previously is I did this, and I would say, okay, we have a single live load, right? Which would just be one of these. You'd still put it at the high point. And then we'd have something like a dead load. What do we do with a dead load? We'd multiply it times the total area, right? No matter what, positive or negative. And then what about live loads? You can start and stop them wherever you want on the beam to create the maximum effect. In this case, it's all positive everywhere. So the live load would be extended over the whole structure. Okay? Any questions about that? We'll do some more, or another one.